Pressure times volume is equal to the number of moles of substance times a constant times temperature. PV equals nRT, the ideal gas law, which works for all gases as long as they behave themselves. Now here's the cool part. Using this equation, we can show how all of these chemists were dealing with the same relationship. They were just clumping various variables together in different orders. All of the chemists we just mentioned, Charles, Avogadro, and Boyle, or more properly Townley and Power, figured out their contribution to the ideal gas law experimentally. But more interesting to me is that it can be understood theoretically. First, we have to understand what each of these variables actually mean. In that same way, the atoms and molecules that make up gases are bouncing against things, applying pressure to them. This balloon is inflated because the molecules are bouncing around inside of it, bumping into the inside of the balloon harder than the molecules bouncing off the outside of the balloon. Scientists generally measure pressure with the SI units of force, newtons per area, meters squared, which is shortened to pascals. But since pascals are so tiny, we either use kilopascals or we use the pressure here on Earth at sea level that we call 1 atmosphere or 1 ATM. Completely by chance, 1 atmosphere is equal to 101,325 pascals, but that's so close that we often just say that 1 atmosphere is 100,000 pascals or 100 kilopascals. Volume is the amount of space particles have to exist inside of, so yeah, that makes sense. When the volume goes down, the pressure goes up because there are more particles in a smaller space and they'll each hit the walls more often. And is simply the amount of gas, the number of moles in the system. Here I am decreasing the amount of gas in the system, and in response the volume is decreasing, obviously, but so is the pressure inside the balloon. R in the ideal gas law is called the universal gas constant, even though, as we will see in a coming episode, it is neither universal nor constant. It's 8.3145 liter kilopascal per Kelvin mole. Temperature is experienced by you and me as hot or cold, but at the atomic level it's kinetic energy, literally how fast or slow the average particle is moving. So if temperature goes up, so will the pressure, as the particles are moving faster, and thus will run into the sides of the container more often.
Welcome to Real vs. Ideal Gas. As you may guess from the title of this lesson, we're going to be talking about what the difference is between a real gas and what we call an ideal gas. We're also going to be looking at what conditions a real gas does not behave ideally, or does not behave like an ideal gas. So first of all, what's the difference between a real gas and an ideal gas? Everything we've talked about so far about gas laws and the kinetic molecular theory has been based on certain assumptions. And we outlined some of those assumptions when we talked about kinetic molecular theory. But the assumptions that kinetic molecular theory makes, and that some of these gas laws are based off of, we know those assumptions aren't true. But we use them anyway, and we call it an ideal gas. So an ideal gas is based off assumptions. And it's important to point this out, that the assumptions we know are not true. One of the things that comes out as a result of this is that the relationship between PV and T, this ratio that we said was constant for a fixed amount of gas, turns out it's not constant for a real gas. That means in reality, the pressure and volume and temperature of a gas do not have a constant ratio. The ratio can change if the pressure or temperature or volume changes. So why is it okay to use the ideal gas assumptions in the first place if we know that real gases don't really behave like that? Well, as it turns out, at STP, a real gas does behave very similar to an ideal gas. So a real gas is kind of equal to an ideal gas. So it's a pretty good approximation with these assumptions. And that's why we use the ideal gas assumptions in kinetic molecular theory and the ideal gas law, as well as all the other gas laws. So if at STP this is an okay thing to do, when does this start to fall apart? Well, real gases behave differently at low temperatures and high pressures. These two conditions, low temperature and high pressure, I don't need to have both. If even one of these things happens, this similarity between real and ideal starts to fall apart. And we see that real gases behave differently. Now this differently means different from ideal. The real gases behave differently than ideal gases when either the temperature is low or the pressure is very high, or both. And there's two reasons why it falls apart in these cases. There's two reasons why the behavior of real gases deviates from the behavior of an ideal gas at these conditions. The first reason, reason A, is that gases in reality have a non-zero volume. Whereas in the kinetic molecular theory, we assumed that all gases, the volume was negligible or zero. The second reason, reason B, is that the kinetic molecular theory says that there are no intermolecular attractions, but intermolecular attractions or intermolecular forces definitely exist. We're going to take a closer look at these two cases. First, let's see what happens when you have high pressure. Here we have a molecule in the middle of this container. You can see it's surrounded by a lot of space, and in relation to the volume of the container, the volume of the molecule is practically zero. So this is ideal gas. This is an assumption that the kinetic molecular theory makes, that this molecule is so small compared to this container that it's practically zero. Now if we apply high pressure to this container or to this system, we're going to see it change so that the size of the container has now shrunk. The overall volume has collapsed in because the pressure is pushing everything in. And now you can see that the volume of the molecule, which has not changed, is no longer negligible. It has a very real volume compared to the volume of the container. The spacing between it and the walls is now not trivial. So that assumption that the volume of a gas is negligible has less meaning when you go under high pressure and the spacing between the molecules in each other and the molecules in the walls of the container shrink. So at high pressure, real gases have more volume than an ideal gas should have. Now let's look at the second case of low temperature. This one's a little trickier to describe, but if we look at an ideal gas on the left and compare it to a real gas on the right, we'll start to see the role of intermolecular attractions. In an ideal gas, we know that the molecule should be moving in random straight line motions, such as this. However, in a real gas, particularly at low temperatures, so at low temperatures, molecules don't have the energy to just fly right past each other. At low temperatures, they're moving much more slowly, so they're more subject to intermolecular attractions. So let's see what happens. We're in the same molecule setup in the real gases, and some are moving. They're all going to be moving much slower. If we look at these two molecules right here, as this one starts to move, and this one starts to move, they're going to come close to each other. When they come close to each other, there's going to be some attraction here. There's going to be some attraction between them. And that's going to change their course. Instead of continuing straight, the molecules are going to deviate. And they're going to start moving in a different direction. So the fact that intermolecular attractions prevent straight line motion, particularly at low temperatures, means that it's going to take slightly longer than you would expect for a molecule to reach the walls of the container for a collision. And those collisions generate pressure. So because of the presence of intermolecular attractions, we see less pressure than we would expect to see because it's taking the molecules a little bit longer to reach the walls of the container and cause a collision. When molecules are moving slowly, such as at low temperature, low kinetic energy, they're moving slowly. When those molecules are moving slowly, they're more susceptible to having their course changed, like in this example here. They're more susceptible to this kind of intermolecular attraction than if they were just whizzing past each other at high speed. So we see this observation that real gases have less pressure than we would expect at this condition of very low temperatures. That wraps up our lesson on real versus ideal gases. Write down any questions you have in your notes and bring them with you to class.
Well, the first thing to keep in mind is that not every solvent can dissolve every solute. Gas molecules don't interact that strongly, so gases pretty much always dissolve in each other. But liquid solvents have a ton of molecular interaction, so the structure of the individual molecules determines whether a substance will dissolve, and how well it will dissolve. Polarity is, of course, the biggest bit of this. For a substance to dissolve, it needs to interact favorably with the solvent. This only happens if they have similar polarities, which allows them to form cool in-solution structures spacing the solute particles out evenly. Now on to the next attribute that affects solubility. Let's assume that you've survived the first course of your meal and you order a soda pop. To get all those little bubbles that make carbonated beverages so refreshing and tingly, carbon dioxide must be dissolved in the water. But how do you shove a gas into a liquid? A gas gets dissolved into a solution the same way David Bowie and Freddie Mercury collaborate. Under pressure. What? As previously noted, I am old. It's not just the pressure outside of the solvent, it's the partial pressure of the solute. Quick review, partial pressure is the portion of pressure caused by the gas we're interested in this case, carbon dioxide. Gas molecules, as long as they have kinetic energy, are going to want to escape the solution, so they will be creating an upward pressure on the surrounding gas. In order to keep the CO2 dissolved, the partial pressure of carbon dioxide in the gas outside the solution has to be equal to or higher than the pressure of the carbon dioxide molecules pushing their way out of the solution. That's why soda bottles are nice and taut when you squeeze them. That little bit of gas up there is pressurized carbon dioxide. And also why, when you open the can, a huge rush of carbon dioxide molecules bubble out of the soda, because the normal partial pressure of CO2 in the atmosphere isn't enough to keep it from escaping. So, to get the carbon dioxide in there, all you need to do is dramatically increase the pressure of CO2 outside the liquid. And this is what's done in soda manufacturing plants. In fact, if you have a soda stream, you can do it right in your own home. Now, it's easy to calculate this change in pressure thanks to William Henry, a friend of John Dalton of Dalton's law of partial pressures. According to Henry's law, the concentration of a dissolved gas equals the partial pressure of the gas above the solution multiplied by a constant that expresses the solubility of the gas in that solution. And we can use Henry's law to figure out how much carbon dioxide is dissolved in our can of soda. The pressure of CO2 in a can is 5.0 atmospheres, and you can look up the solubility of CO2 in an aqueous solution, 3.4 times 10 to the negative 2 moles per liter atmosphere. So the concentration of dissolved CO2 is 0.17 moles per liter. Now, there are 355 milliliters, or 0.355 liters of cola in a can. How much volume would that CO2 take up at normal atmospheric conditions? Whip out your trusty ideal gas law, and we find at atmospheric pressure and 298 kelvins, or room temperature, 0.060 moles of carbon dioxide will expand to about 1.5 liters. That's a lot of burps. Something else to keep in mind on date night. Finally, in addition to polarity and pressure, it's temperature that affects solubility in the most complicated and therefore interesting ways. When we're dealing with solid solutes and liquid solvents, their total solubility generally goes up as temperature increases. This is a fact that you already know if you've ever tried to put a bunch of sugar into your iced coffee. The solubility of gases, on the other hand, is the exact opposite, because colder molecules have less kinetic energy and are less likely to escape the surface of the liquid. So the upward pressure they exert is lower than it would be in a hot liquid. That's why it's safer and cleaner to open a can of soda pop when it's cold rather than when it's hot.